I'll try to remind you as an email, but I really can't remember for you. You got to try to write it down yourself. What are you missing, guys? Ray went to the bathroom.
It was Thursday.
You thought today was Thursday? I thought today was Thursday all day.
If you didn't have like a growth.
I'm sorry.
If there was no growth.
Chris Conte. No, Chris Dragon. It's Chris Bell. Chris Conte is Dragon. Dragon. Yeah, that's what it is. Okay. All right, so we're going to review today. Test 21, pretty much, right? Chapter 21 is what we're looking at here. So we're looking at 21.1, which is all about current and resistance. 21.2 is about circuits. And 21.3 is about power. Okay, those are our main three topics that we're focused on. Let me start by asking, did you have any questions on the problems that you want to go over? Anything that confused you or stumped you along the way, we might get a good review time for today. Yeah, Ed, we're ready first.
Verse 7.
Page 776, number 20?
Yeah. No, number 7.
70.
It's like a circuit.
Okay, it says, this is the word problem, right? A fuse is a device to protect the circuit from the effects of a large current. Is this the right problem? Yeah. The fuse is a small strip of metal that burns through when the current in it exceeds a certain value, thus producing an open circuit. What's another word for a fuse? What's another phrase that we've used in this class for the word fuse then?
A circuit breaker.
Circuit breaker, that's what this is. So it's a circuit breaker. And these are the old circuit breakers I was telling you about, that when the fuse blew, it was like a little piece of glass, the metal strip was inside of it. That metal strip would burn out, and then suddenly there would be no way for the electrons to continue flowing through the circuit. So that metal strip was specifically made so that above a certain amount of current, it automatically burns out. Okay? So let's read the question. It says, thus presumes A, should a fuse be connected in series or in parallel with the circuit board it's intended to protect? Series or parallel? What do we think for this? That's a good question. Should the fuse be in series or should it be in parallel?
I say it should be in series.
How come?
In parallel, they share like voltage. Like if one goes out, it still keeps going. But if it's a series, it goes all the way through, and you need a fuse to like stop that.
Correct. So in series, if one resistor goes out, it creates an open circuit. But in parallel, if you remember the branching off, if I lose this resistor, I just lose that branch. But all the other branches of the parallel circuit come back together. So it's a series circuit for sure that you would hook up your fuse to, so that when the fuse blows, the energy stops flowing through.
Should we go to parallel one though? Because you just want to isolate like a specific part.
Well, that doesn't say it though here. Read what it says. Read carefully. It says, should a fuse be connected in series or in parallel with the circuit it is intended to protect? So we need that fuse to be in series for that one circuit. Every other breaker in your box, when you open the box in the hallway out there I was telling you about, every breaker is its own circuit. So it's not like we want like a million fuses all in parallel. Each circuit is separate. So we want those fuses to be in series with that individual circuit. Then the next breaker has its own fuse in series with its circuit. The next breaker, those little switches, each of them individually. The second part says choose the best explanation. Okay, yeah. So what we want is for series, so it opens up the whole thing. It's a good question, because I can see how that can be confusing, because there are several of them. You don't want them all to go out, right? Each of them is on their own individual circuit.
Can we do 86 on that same page?
86 on 777, the next page. All right, so it's a circuit, so I'm going to draw it real quick. So we've got terminal A, terminal B. We don't have a battery in this problem. Okay, we're just given the actual points A and B. We're started with two resistors like that. Everything is in units of ohms. I'm just going to put numbers for now. Everything has units of ohms. Then I'm given this part here. And then this guy branches off. Okay, great question. I can see how this can be a little bit confusing because of the nature of it, right? The nature of the setup in this problem. So, first, where do you see imagine the batteries A and B always, okay? When they show these diagrams without batteries, imagine the electricity flows out of A or B. Starting with A. So literally look at A, and from A, try to get to any resistor without a branch. Is it possible? Can you get to any resistor from A without branching? No, you can't. And if you follow, watch what I'm showing here. The current, say this is the positive terminal of the battery. The current leaves the positive terminal, and when it gets to the first branch, it literally branches off. So again, the current is flowing out of part A, let's say that's the positive terminal. It hits that branch and it branches off. So right away, we know that this major circuit is in parallel. The major circuit, meaning the whole thing. So with me so far? Now, these first two are clearly in parallel with each other because we see a second branching off here. Now, what I want you guys to do is visualize, what if this entire thing right here, take a look where I'm circling, what if this entire thing was simply this? Make believe this wasn't here. Again, in your minds, real quick, make believe this isn't here, okay? And you only have 1, 2, 3 resistors. Would they be parallel, series, or both?
Parallel.
They'd only be parallel. Again, without this little branching at the top, we'd have 3 resistors all in parallel with each other. Okay? What I want you to recognize is that these 3 are also all in parallel with each other. Take a look at the top. We have this branching off, but then we have another set of branching off. So these 3 are in parallel to start. And if I can make them one resistor right here, then the one resistor that they become is in series with this guy right here. Again, take these 3 in parallel, make them into one resistor using your parallel law, and then if you follow the current, it would go through that one resistor that's here, it would go through this resistor here, which makes these 2 in series. We can combine the ones in series, have one resistor, and then these 3 would be in parallel. So my recommendation, again, is to resolve anything in series, but nothing's in series to start. Okay, if I only had the 3.3 ohm, if I didn't have the 8.1 and the 4.8 at the top, the 3.3 and the 6.3, those would be in series, wouldn't they? Again, imagine I don't have the 8.1 and I don't have the 4.8. The 3.3 resistor and the 6.3 resistor, those would be in series. But because these 2 things are here on the outside, these 3 are in parallel. So let's resolve this parallel component into one resistor here, and then these will be in series, which we could resolve them into one resistor, and then these 3 would be in parallel. Does that make sense, the order in which I'm saying? So let's do the first part together so we can see the parallel part. 4.8, 3.3, 8.1. How do I find the equivalent resistance when in parallel? Yeah, you missed the beginning part though. Right? 1 over RP equals always, right? So 1 over RP equals 1 over 4.8 plus 1 over 3.3 plus 1 over 8.1. I agree. I'm not doing the math right now. Add this together on your calculator. See what you get. Then take the reciprocal of that to get R cubed or RP, whatever we're looking for here. Again, if you add these 3 together, you'll get a number, but we want that number RP, so we have to switch these 2, which really means take the reciprocal. What do you get from this?
1.5.
What is it?
1.58.
1.58. And how do I know that Steve's answer is reasonable? Who remembers what we talked about? Think back to your notes if you have to. How do I know that Steve's answer is reasonable? This is a great multiple choice question for tomorrow's test. How do I know that his answer is reasonable?
Because it'll always be less than the resistors.
Any of them, right? Any resistor in parallel, when put together, has an equivalent resistance that will be less than any of the original 3 you started with. That's not something that's a coincidence. We talked about that in class. When it's in series, we add the resistances together. So the answer is always greater than the largest of them. But in parallel, our answer will always be smaller than the smallest of them. Yes, sir?
Just a question about the math for this. To solve for the equivalent resistance, can you just add up those 3 and then make it to the power of -1?
Yep.
Okay.
Inverse, reciprocal. Same word for that. Yep. Power -1.
So the REQ is smaller than what?
any of the original 3 in parallel. And those 3 are 4.8, bless you, 4.8, 8.3, bless you, and 8.1.
Okay.
So these are the original 3. The smallest of them is 3.3, and yet this is lower than that. It will always be true for parallel circuits. Parallel circuits. Okay? All right, so we've got an equivalent resistance for this section right here. Let me circle it in yellow. So this section up here, I can replace with one resistor of resistance 1.58. So let's redraw the circuit now on the right. Let's redraw the circuit. 1.5, 2.5, 1.58, and 6.3. So here's my new circuit, or my simplified version. Am I done? Obviously not, right? I'm only done when I have one resistor at the end. Only with one at the end. So next, look for branching. There's still branching right here, which puts these 2 in parallel for sure. And then there's branching here again, which puts these 2 in parallel with whatever the third one is. I don't have one third one, I have 2 of these. How are these related to each other again? They're in series. Because to get from the 1.5 ohms to the next one, no branching occurs. So I know that the 1.58 and the 6.3, the flow, watch the flow of electricity, I'll point. The flow of electricity does this. It gets here, and it splits between these 2. It gets here, it splits between these 2. Now, it continues here into this one, comes back around, this flow comes through, this comes back around, they join together here, and they continue here. Then the flow coming out of here joins with this one, meets and merges to continue here to B. So what you want to recognize is that when it gets to 1.58, it continues without branching all the way through 6.3. So yes, these are in series. Because they're in series, the math is simple. You don't need to show the work for that. Just sum them together in series. So 6.3 plus 1.58, 7.88. Okay, is 7.88. So my new circuit will look like this. 7.88, 1.5, and 2.5. Okay, so again, we've taken those 2 in series, I'll circle them in green, and replace them with 7.88. And the last step is to recognize that you now again have one parallel setup with 3 resistors, but they're all in parallel. Ready? Comes out, branches. Comes out, branches. Gets to the next one. So these 3 are all in parallel. 1 over 1.5 plus 1 over 2.5 plus 1 over 7.88 equals 1 over RP. Same exact law we used a minute ago in blue. Okay, 1 over RP equals 1 over 1.5 plus 1 over 2.5 plus 1 over 788. I know that my answer is going to be less than 1.5. Okay, I know that already because of the nature of the setup. What do I get? Anybody have this number for me, or anybody finish this? What'd you get for this? Point what? 0.838. I see nods or yes, maybe? Yeah? Okay. 0.838. Okay, so really, that's my answer. But if I want to draw the circuit so we can see the final answer for the circuit itself, just draw yourself a little circuit with A and B. And draw the one resistor of 0.838 ohms. Okay, it looks like this is an open circuit the whole time because they're not showing you a battery. But whenever you're given an example where you have terminals A and B, you assume that these are terminals that you're going to hook up your power source to. So one wire goes to A, one wire goes to B, and therefore electricity flows. Okay, it's like a battery's in between them.
So is it easier to start with series?
Anytime you can start with series, you should, but because at the beginning we had nothing in series, we couldn't.
Okay.
Once we simplified what's circled in yellow, then we had stuff in series. But yes, anytime you can simplify series, right away do it, because you're just adding them up. Then go to your parallel branches. Then when you simplify parallel, you might have another series or something else, and then go from there. Yep. And I definitely recommend practicing this. You can practice it and infinitely many times. You can literally just draw your own diagram every time, right? Physically, just draw a new diagram. Vary this a little bit. Maybe put 2 or 3 resistors here. Put another branch coming off of here. Just change up the diagram and redo it. And see what you get as an answer. Obviously, I know it's tough to check your answer because there's no answer key. But you could at least try a bunch. You could also look in your text and see that there's a couple. 80, 82, that was 86. If you go further, a little bit further on, some of these mixed review would not be bad. But even at the end of the chapter, hey, look at this, page 781. A bunch of multiple choice questions. Not a bad idea to use for study. You guys noticed this by now? At the end of every chapter, there's multiple choice. So if you want to look at the multiple choice at the end, that's a pretty good idea, page 781. Okay, there's a bunch of other examples there as well. Very good examples for the test. Other problem set, next hand up. That was Sarah's. Same one? Okay. Other problem set questions. These are good questions, guys. And I'm glad we're doing these because in the other class I reviewed everything that was on the test and we ran out of time to get to any questions. So if you want like a real overview of the whole test, their recording from section 1, I literally just overviewed every section we went through. I didn't do much math in that section though. So this is more math actually, which is good. You can tell them if they want to do a little studying for math to look at your video later. We did a lot of theory in the other section. A lot, almost all.
Can you go over number 72, same page?
Okay, number 72, page 776 says the following. 2 resistors are connected in parallel. Great question, Alex. If a third resistor is connected in parallel with the other 2, does the equivalent resistance of the circuit increase, decrease, or remain the same? Now, you had a homework problem a couple days ago that said how many resistors should be set up in parallel so that the equivalent resistance was like less than 11 ohms or something to that extent. And what you noticed was as you put more in parallel, the overall resistance went down. As you put more in series, the overall resistance goes up. Okay, that's always going to happen, and you can check this by just trying numbers. Okay, so if I had 2 of them in series with 10 ohms, the equivalent is 20. If I have 3 of them in series of 10 ohms, the equivalent is 30. 4 is 40, 5 is 50, etc., etc. Because series, you just add them up. In parallel, though, that's an ugly one. Start with 2. In parallel. Make them both 10. What's the equivalent resistance? 1 over Rp equals 1 over 10 plus 1 over 10. That's going to give me 2 over 10. And the reciprocal of that is 10 over 2. So Rp will be 5 for this. Now what if I have 3 resistors all the same? Add 1 here. That becomes 1 over 10 at the end, doesn't it? Now it's 3 over 10. So then I take 10 over 3. 10 over 3 is 3.33. So what happened to my equivalent resistance? It went from being 5 when I had 2 resistors, and then I went down to 3.33 with 3 resistors. If I added a 4th resistor, it would be 2.5. If I added a 5th resistor, it would be 2, because I'm continuously adding 1 to the numerator and then reciprocating or inverting that. So as you add more in parallel, the overall resistance goes down.
It's confused me on the problem set because I just added them at first and I was it increases, but then I thought you had
That's in series.
Right. I remember
You have to reciprocate or invert them, yep? So again, if you just add these 3 together, you'll get 2 out of 10. Then you'll get 3 out of 10. Then you'll get 4 out of 10. So it seems like it's getting bigger, but you got to remember to do the reciprocal. Okay? And that's a good thing to remember as a general theme. A theme, right? An idea that as you increase the number of resistors in parallel, it goes down, but in series it goes up. Okay? Good ideas. Because if you're given a question on the test, you don't want to have to do this, right? You want to understand the concept more than having to rely on the math. But you can do this if you need to, which is why I keep saying it's really important to use your formulas on the multiple choice also, not just the end of the test. A lot of you use the formulas only on the math, but the formulas can really help you on this test especially. Remember, we have 6 formulas for the voltage, current, resistance, voltage, current, resistance, 3 series, 3 parallel. Then we've got 3 formulas for power. We've got Ohm's law that says V equals IR. That's 9 formulas for this test. of which you're probably not going to use most of them on the math part. It's really the theory that will help you with. Okay? If you forget that the current in parallel branches off, just look at the law. IP equals I1 plus I2 plus I3. A sum law, which means they must have branched off at some point in time. Okay? 102. A 94 ohm resistor. So right away, 2 words, and I have that. A 94 ohm resistor, 2 words and a number, is connected to a 15 volt battery. How much energy is dissipated by the resistor in 6 minutes? Ooh, this is good. I like this. So the time is 6 minutes. And the question is, how much energy is being used? It's a great question. I can't find the energy being used right away because energy, unfortunately, is not one of these formulas, right? But what do I know from this section about energy? What is energy equal to if we want to think about a formula? What can we replace energy with? What variables? What times what? What can energy be replaced with? What times what? Times?
Time.
Times time. Very good. Think back to this formula here in the top right. Power is the change in energy over time. So if you want the amount of energy, you need the power times the time. So really, we're looking for the change in energy. We have the time. What do we really need is the power. Again, if I have the time already and I can figure out the power, I can find the change in energy. This is not a cost problem. I don't have to worry about kilowatts and hours. It's not a cost problem. So I'm going to use my standard units here. What's my standard unit for time? Seconds. 6 minutes is how many seconds? 360 seconds. And at this point, I can go ahead and figure it out. So if I need power first, so to get energy, I'm going to use power times time. So let's find the power first. Power equals 3 formulas. Which one am I going to use for power? I got 3 formulas. Which one, Sarah? How come, Sarah? Yeah. This problem has to do with the voltage and resistance in it, in the circuit. So I'm not going to use P equals IV. I'm not going to use P equals I squared R because I'm not given anything about I. I'm given V and R. This will give us the power. Once we have the power, take that number, plug it in right here, take the power times 360, and you'll get the amount of energy in joules. Is that good? Is that an answer? Yeah. Very good question. All right. Anything else on the problem set? Alex?
So wait, once you find power, can you convert the watts into kilowatts?
So only the cost problems involve kilowatts because the rate you're charged is dollars per kilowatt hour. So the only time we're converting watts to kilowatts and seconds to hours is when it's a cost problem. Is that clear what I mean? Okay?
So you just multiply the power times 360 and then that's it?
Yeah, that's it.
What if you convert it to kilowatts?
Then you would get an answer in kilojoules, which is fine, but you'd have to write kilojoules as your unit. So if you use kilowatts as your power and then multiply that by 360, your answer is something kilojoules instead of just joules. Yeah? Okay. Marco? No? You had a hand up for a second?
Oh, no.
Okay. All right, let's think about what else we have to talk about. Let's talk about some theory then. We did a little bit of math problems here. Let's go back to 21.1, the first section. In the first section, we defined current and resistance, right? Current is the flow of electricity, right? The flow of electricity or the amount of charge, Q, we called that charge. The amount of charge passing a given location in a given time period. It's like the amount of water flowing through a pipe. And then resistance was the opposite of that, right? The resistance slowed down your flow or it regulated your flow. The resistance opposes your current. The resistance opposes your current. Now, within that section, we talked about several things. We talked about things that could vary in resistance, and we called those pentiometers. In a pentiometer, a simple example, does anybody remember the example I gave? What was the example, Maria? Go ahead. Yeah, any dimmer. a volume dimmer, a light switch dimmer. On the circuit board, as you guys did this, if you recall, it was this little thing right here that you could turn. Okay, that was your potentiometer. It was a dimmer. I don't think any groups got a chance to get to that, but I mentioned that if you network bulb C into it, you could actually, Steve, you guys did it, or you were doing it. That's what it was C, yeah. But you could vary the dimness of the bulb. And you see this at home, right? When you have the little switch on the side of here. Let's see. That was potentiometer. I talked about superconductors. What was a superconductor? I mean, don't give me the exact definition. Tell me in your own words. What was a superconductor? What was the idea behind it?
Isn't it just like something that accelerates the conducting power of something?
Okay, that's a good way to put it. It helps with the conducting power.
Kinda
So if
like-
it conducts really well, it has very little what?
I was going to say it's kind of like a catalyst.
Okay, that's a good word for it. Catalyst. I like that. Catalyst. But if it has very, very good conductivity, what does it therefore have a very low amount of? Resistance. So a superconductor is a material that exhibits almost no resistance to electrical flow. Almost no resistance to electrical flow. Now the caveat is that most superconductors have to be held at a temperature that's extremely low. Like 2 kelvins, 3 kelvins, very, very low. So as a result, it's not very commonly occurring. There are not many superconductors that exhibit that superconductive property at room temperature. So it's not as useful of an application yet. A lot of the goal in science right now is to find materials that are superconductors at regular temperatures. I also talked about 4 factors that affect resistance. Give me some. You don't have to give me all 4. Give me one of them at least. What is one factor that affects the resistance in a circuit? Or the resistance in an element, I could even say, in a certain given element. Kevin? The length of the wire, right? The length of the coils or wire. If you have more wire, you have more chances of collisions between the electrons and the atoms, the copper atoms, let's say. So if you have more length of wire, you have more resistance. They are directly related. That's 1. 3 more. Temperature. Do you remember how they were related? I gave the example of a computer. I talked about computers. How is temperature and resistance related?
The more harder it is, the less resistance.
The hotter it is, the
more resistance.
the more resistance it has. So what do we say? They are, the hotter it is, temperature goes up. The more resistance goes up. So they are directly related. Again, more temperature means the computer is going to go slower. It's because you're exhibiting more resistance to the electrical flow. And that's just an analogy. It's not exactly what's happening in a computer. I'm just giving you an analogy there. So again, temperature is directly related to resistance. Length of the wire is directly related to resistance. Those are the 2 that were directly related. What else? What are the 2 properties? Material itself, very good. And that one we can't come up with a relationship because it depends on the material. So if I use copper or silver or gold or aluminum, it's going to change the amount of resistance in that resistor. So the material properties, but there's no direct or indirect variation given there. Last, I'm reading off the chart, obviously, you guys know, right? Now I'm thinking off the chart. The chart was in your notes for 21.1. There was a 4th thing that affected resistance. Yeah, cross-sectional. What's the math word from geometry? Cross-sectional area. Remember that if I have a tube that carries water, the area that is open to flow is the cross-sectional area. How many of you guys, well, a lot of you probably use regular bread, but if you ever get a loaf of bread that's not sliced, when you slice a loaf of bread and you look at the bread, that's the cross-sectional area. Okay? Be careful, we might have fallen into there. That's the cross-sectional area that you're seeing. When you physically take a pipe, imagine a pipe flowing under the ground, and you cut through the pipe, and you open up and look at the circle, that circle is the cross-sectional area. So the more cross-sectional area, think about it this way. It's pretty easy for the electrons to flow because there's more room, right? So those are indirectly related. The more cross-sectional area, less resistance to flow. less resistance to flow. Indirectly related.
It's kind of similar to like surface area.
Give me more.
Like the larger the surface area is, like the more room there is to go around. It's like more spread out.
Sure.
The resistance
Yeah,
is like
and
more spread out.
it's similar to any area,
Right.
Peter. So the area of a triangle, the area of a rectangle, any area in general. Okay, it's more spread out. That's good.
Cross section is also what kind of
A little louder.
like cross section is also used in biology when looked at like I guess like an animal.
Yeah, you take slices of the cells
Yeah.
so you can see what's physically happening in the cell. Absolutely. Yep. Guys, cross sections and slices. If you want to take calculus, or you're going to take calculus in college, or even advanced physics, you're going to do a lot with that, a ton. Where you take, like, imagine a baseball bat, right? Imagine a baseball bat sliced up into little pieces. In the beginning, where the barrel is, the part you hit the ball, versus the handle where you hold it, where the barrel is, they're big pieces, aren't they? But as you get to the actual handle, it's tapered, meaning the handle gets smaller, and then it kind of gets bigger at the end, at the knob. So if you took a baseball bat and sliced it into like 100 little pieces, or a softball bat, you would physically get a bunch of different circles. In the beginning, they would all look the same. But then those circle areas would get smaller and smaller, and then at the very bottom, the area gets a little bit bigger. But this concept of taking slices of things will continue to present itself in pre-calculus, AP calculus next year, AP physics next year. Any of those courses that you will most likely take one of those three. Pretty much everybody in the room will take those courses. So cross-sectional area. That's it for 21.1. In 21.2, we kind of covered already a lot of it, but I want to talk about some specific things. Let's first start with the diagram or definition, either one, of a short circuit. What is a short circuit? Give me a diagram if you want. Either way, how would I draw a short circuit, or what would a short circuit physically be?
So like a battery, and then once you draw the wires, like an opening, like a switch. Yeah.
So that's an open circuit. That's all right. These words are very commonly used in change of each other, but they're not the same. So this is an open circuit. We'll start with that. So Alex gave us what an open circuit is. If I close the switch, then it's a closed circuit. Closed circuit. Marco, pay attention, please. It's closed circuit. If I want a short circuit, though, a short circuit, what is a short circuit here?
I just think of literally creating a short path for
So how would I create a short in this one?
you took the two walls on the left and right and just connect those.
Yeah, if I did something like this right here, boom, that blue line is a short circuit. Because here's what's going to happen. The electrons are going to flow out of the battery. They're going to want to go into both parts of this circuit. But because there's no resistance here, electrons always take the path of least resistance. They will all take this path, and this will not actually be involved. Another example of a short circuit is physically not having any element besides a battery. That's your best example of a short circuit. Okay, if you physically connect a battery to a wire and let it sit there forever, that wire will continue to heat up. The energy that the bulb would be using will be used instead by the wire. Peter?
Wait, so how come if you like had put a light bulb on that line across, that would not be a short circuit then, right?
Because there'd be a resistance there, and that light bulb would take on the energy from the charge carriers, whereas here, the energy from the charge carriers just goes into the wire, and that's the idea of a short circuit. It's when the wire is the only thing that can hold on the energy, and a wire can't hold that energy.
Oh, okay.
It's too much for the wire.
So that's the same as that.
Yeah, these are the exact same
Oh, okay,
things,
okay.
but if I added a bulb on the blue area, Peter, then the bulb in the blue area would take on the energy, and the blue wire would not get fried instead.
Okay.
Okay. Let's see. Short circuit, open circuits, laws in parallel and series we've gone over. Yeah.
Which one's the one where like we have a light bulb and the wire in the light bulb like breaks? Is that a short circuit?
So there are two. Yeah. So it could be either. So we looked at the diagram of the light bulb, right? If the filament inside the light bulb physically burns out, that's creating an open circuit. Because now the electrons cannot flow through the light bulb anymore, and there's an open gap there. But if you have wires that are going into your light bulb, and those wires, before they go into the light bulb, get crossed or touched, then that's a short circuit. Okay? I'll show you a quick diagram of that to make it more sense. So, let's say we've got, I'm going to draw a really crude version of a light bulb. Here's the filament right here. And there's the wires coming out. Okay? If the filament physically, so this is connected to a source. Okay, remember this? Guys, I don't know. I know. Just ignore it. I know. This is normally a battery with a circle around it. It represents a plug in the wall. So the plug in the wall is connected to this light bulb. This creates a closed circuit. If I physically do this, take a look at the board, please. If I physically just erase my filament, look at my filament now. Now this is an opening in the circuit. So the electrons can no longer flow. That's an open circuit. But instead, as Catherine asked, if for some reason the wires get frayed, and the wires, let's make them different colors here. Let's say this is a red one. The red wire comes loose, and this blue wire comes loose, and they happen to touch each other before they get to the bulb, that's a short circuit. Because the electricity will do exactly what we were talking about. It will take the path of less resistance. When it gets to here, instead of continuing to the bulb, it'll take the least resistance here, and it'll come right back into the actual source. And that'll create a short in the circuit.
Nothing actually happens if you do that. Like, it doesn't, like...
Instantaneously, no. But it will over time. So
I've done
if
that
you literally
before.
touch it, you might see little sparks, but I mean here specifically, these wires will eventually start to heat up.
Like, the battery just gets hot, yeah.
The battery and the wires will gain heat,
Yeah.
and they can then, cause a fire. Do we want it, Steve? You want to check it out for us? Just give us. We don't all have to get up.
Give us the lowdown.
It's much farther down that.
But is it down the avenue or is it down the street, Steve?
There are cops over there. They're lined up.
Oh, it's definitely
What is it though?
it's definitely like a
People walking down the avenue.
Is it a protest?
looks
It doesn't open
like-
anymore.
This way.
They, guys, those are all locked. They don't open on purpose, so you can't stick your head
See,
out.
look, they're walking down the street.
It's so that you don't fall.
They're walking down the park avenue.
I'll tell you what it is right now. Let's see.
Check Twitter.
Check Twitter.
I was gonna check. Maps tells you too. Yeah, Maps puts parades on there now.
What maps do you use on Twitter?
I don't know if it'll do this kind of parade though. Let's see. Nah, it doesn't show it on Maps on here. Sorry, I'm wrong. Usually, for marathons, it shows up as a little red dotted line on your map. On Android maps.
Yeah, I was gonna say.
All right, grab a seat.
Park Avenue South is
We have to leave in like 10 minutes for that. I'm excited.
What? Yeah.
Does it say what it is?
No.
I'm gonna check Twitter.
Check Twitter. Hey, what else? So the cost is equal to the power, the energy, Jesus, times the rate. I'm doing this off the top of my head. Energy times the rate. But the energy is defined as power times time. So when we're finding cost, we can use power times time times the rate. Okay, recognizing that the power has to be given or stated in kilowatts, time has to be stated in hours, and the cost is dollars per kilowatt hour. Okay, all yielding units of dollars for cost. Okay, pretty important to be able to utilize this. Recognizing, though, that I might have you for part A calculating the power, and then for part B calculating the cost of that much power for a given time period. Okay, so you'll have multiple step problems for sure. I'm guaranteeing you that now. You'll have A, B, C for the math type problems. Maria. I can't say it louder.
You know that on past tests you would put up like problems to do online that like you like word problems like on past tests it'd be like multiple practice problems.
It's like all they
Can you
do.
do that?
They look forward.
Like suggested problems to practice?
Yeah. Or like you would give us
Sure.
a problem. Like you would, yeah. It was like
I don't have anything made for this, and honestly, I don't have time to make it tonight. But can I recommend something then? Because I'm looking at your text right now. So I would recommend looking at page 781 for sure. It's just standardized test prep questions, all it is. And then the mixed review on page 778. On page 778, there's a couple mixed review problems. Aside from that, Maria, honestly, I would look at, the lesson checks at the end of the chapter, and then how there's these practice problems in the middle. There's a lot that we haven't done, so it's honestly, you can do all of these. There's nothing we haven't covered in this chapter. Everything problem-wise we've covered mathematically or conceptually. So for now, I would just hypothetically recommend that you do practice problems, lesson check, and then the end of the chapter standardized test. I don't have time to make it tonight. In the past, I had those made already. That's why I put them up there. Okay, but I'll be honest with you, I don't have the time to make that one. Other questions?
And this cost formula is not on
I think it is. Check your formula sheet. I think it is.
Sweet.
I think it's at the very end of the electricity topic. Is it not there? No, you're right. It's not here. I thought I had it on here. V equals IR, T equals I dash square over square over R.
Zucchini.
No, it's not on here, guys. I thought it was. Please memorize that cost equation, energy times the rate.
Aw.
It should almost be common sense because of the fact that if you think about the cost of anything, it's the amount you buy, energy used, the amount you use, times the cost per item. Remember I said apples? I was like, if you buy 5 apples and it's 25 cents an apple, this is the amount of apples bought, or the amount of energy you physically bought that energy. The amount of energy you buy times the cost per energy. So energy times rate gives us this. Energy is power times time. I thought it was on there. I don't know. It may have been in the past, and maybe I removed it. It's possible I removed it, or I just forgot. Okay, it's also on page 771, right here. Cost equals energy used times the rate. Okay, cost equals energy used times the rate. Good? All right, you guys can go.